Hello, can anyone, if someone could write if they can hear, that'd be great. So we're going to start in a minute, but if you could just let me know. Whee! Okay, good. We'll start in a minute then. This is a brave new world, isn't it? I'm going to be one of these YouTube influencers before long. I know you're all excited for this. We'll just wait a minute. Yeah, so you can ask questions on here as we're going through. So we're going to let's get it all. Okay. I'll put that so I can get as much. Here we are, 1 minute then we'll start and then why does it do this? God, it's fiddly doing this. Okay, so we can start. Oh, not this again. One sec. So yeah, there's a slight feedback delay on the chat, but it is, if you want to ask questions, you can on there. So this is tutorial 1, so we'll cover the questions that we didn't get time to go over in the tutorial, and we'll give a bit of background as well. So question 1 is asking you to derive the ordinary least squares estimator in a simple regression with just an intercept and one scalar regressor, xi. Now, sometimes it can get confusing when they write it this way. We don't actually need to assume all this. We don't need to assume a random sample or a linear model or any of this. Namely, the OLS estimator has just got a general definition. It's just, you don't need to say this. Whether or not the true model is linear, whether or not there's multiple linearity, whatever else, the least squares definition just says, the definition of OLS, we specify a linear model. So in this case we've got two parameters, b0 plus b1 xi, plus it specifies that y is linear in all the regressors and parameters plus a residual. And technically the residual is a function of b0 and b1, of course. For every different parameter we're going to get a different residual. So OLS, the definition of the OLS estimator, stack it into a vector, so b0 hat and b1 hat, is just, the fancy way of writing it is, it's the argument or the parameter that minimizes across all values of b0 and b1 the sum of squared, the average sum of squared residuals, this yi minus b0 minus b1 xi squared. Sometimes we put the 1 over n there, but it doesn't matter. Sometimes it doesn't matter if you put this there or not. It's not going to change the solution. Sometimes we keep it there, sometimes we don't. So we can just drop it for now to make it simpler to derive, but it's not going to change the solution whether or not we multiply by a positive constant. So this is its definition. So this is the definition of the OLS estimator in a model where we include an intercept and one scalar aggressor, xi. So we're just choosing b0 and b1 to minimize the squared sum of this, which you can just think of as fitting a line to a set of points. Optimally, you've got a set of y and x in the sample. You've got a sample from I equals 1 to n, so you've got n data points, like n equals 100 or whatever else, and for every line you specify, so you're going to pick some particular b0 and b1, so b1 is going to be the slope of this. There's going to be distances from this line to the residuals, and you keep varying this curve to minimize that distance. So think of this as just a loss function. It's how far this particular line, given for b0 and b1, fits to the set of points y and x. Okay, so we'll come back to how you interpret what this actually estimates and what it does, and its properties all depend on the condition, linearity and exogeneity and so on. But its definition is just this. It's got a mechanical definition. It fits a line to a set of points. We then just have to then solve this. This is just a function of this here. Really, you can call it just whatever, fn alpha. Sorry, b0 and b1. You put n because it, of course, it depends on n. b1 and b0. So it's just a function of n. It's just a convex function of b0 and b1, a quadratic function. So of course it's going to have a unique minimizer. Okay, so it's just a function. So again, once you've got the y's and x's there, then fixed, you've got a function of b0 and b1. So the y and x are known to us. Are going to be a stream of numbers, and then we can evaluate what this function is, every value of b0 and b1, and then choose those parameters to optimize and find the minimum. So we first take the first order condition with respect to b0, and again it's unconstrained minimization here. You just take the first order derivative. So we differentiate this function, call all of this here fn this. We're going to differentiate this with respect to b0, fn b1 equals not, and again we're going to have a first order condition for b1. So again, this fn just shorthand for this sum of squared residuals. You could call it SSRN, I guess. That's probably a better name for it, the sum of squared residuals function. And that's it. You can do it. You're going to get two first order conditions, and then you can solve. And the solution to these is going to be the b0 hat and b1 hat. And we already know there's going to be a unique solution because it's a strictly convex function. So if we take the first order condition then for b0, well, differentiate. So again, when we differentiate the sum, so I'll give the full detail here because it's never clear how many of these steps when we skip them is confusing. So I'll run through the whole thing. yi minus b0 minus b1 xi squared. So this is what we want to differentiate all this. Well, the sum doesn't depend upon b0. So this differential of the sum is the sum of the differential. So this here is just n of these functions added together. One for each. You're going to be, for each, if you're going to get y1 minus b0, b1 x1 squared, plus then for x, y2, and then for 0.3 and so on. So if we've got the sum of n terms, all functions of b0 and b1, well, when we differentiate, we're going to differentiate each one together. So it's this differential satisfies the additivity property. So it satisfies this. d by db0 yi. And then we just differentiate within. We're going to use a chain rule. So you first differentiate the whole thing. You're going to get 2 times what's left inside, and then multiply by the derivative inside. So you differentiate the squared function first, and then multiply by what's inside. So we're going to get sigma I equals 1 to n. So we're going to get minus 2 here. We're going to differentiate with b0 first times yi minus b0 minus b1 xi. Remember, we're choosing b0 and b1 now equals not. Well, yeah, okay, we're not. That's just what we're going to set that equal to naught. So we're just for now just okay, which equals minus 2 I equals 1 to n. Okay, and we're going to set that equal to naught. So we've got a first order condition. So the first order condition then for b naught, we can rewrite that. Setting this to naught is just going to be sigma I equals 1 to n yi minus b naught minus b1. And we're going to solve, remember, for b naught sets this to naught. So that's one condition. And we can see we can multiply both sides by 1 over n. It won't change anything. What this is saying is we're choosing these parameters. It's going to make the sum of the residuals equal to naught. And remember, that's what we want to do because we're going to assume that the average of the residuals is not at the true parameters. So we're just forcing the sample version of that. So this is the first order condition. You can solve this and get the b naught hat as a function of b1. So you can solve this. If you take the sum through, you're going to get y bar minus, well, the average of b naught is itself because it's constant. So again, the average of the sum of 3 terms is the sum of each one together. And again, don't get confused. We can always we're not going to change anything by dividing by 1 over n. It's got the same solution. It just makes it often easier to work with. You can do it all afterwards, so it doesn't change the solutions. It's all equivalent whether or not you multiply by 1 over n. It will not change the solution to this function, to this equation. So we're going to get minus b1 and then take the average through, minus x bar equals naught. And again, this is what's going to hold at the optimal. So we're going to get b hat naught as a function of b1. So we can solve this. This implies then that the optimal solution for b hat naught, say, for a given b1 is equal to y bar minus b1 x bar. So to be fully formal, all we've done is worked out b hat, the solution for whatever b1 is, this will be the solution for b hat naught. So we can then use this then in the next first order condition. This is what the first order condition gives us. So you can tell we can't identify or work out what this is without another condition. We need something else to pin down b1. Well, we're going to get that from the second first order condition, which is just now this. We've got d by db1 of, so again, take the first order condition. So again, we'll go a bit faster through it now. Well, this is just going to be, we're going to set this equal to naught. What we're going to get from this one is we're going to get sigma I equals 1 to n xi yi minus b naught minus b1 xi equals naught. That's going to be the first order condition. Again, we divide out the minus 2, so you're going to get the minus 2. We just skipped a few steps, do the exact same thing. All it's going to differ is we're going to get a different differential inside. So now we get this, and we can take it all through. So again, you can multiply both sides by 1 over n. It won't change anything. Okay, and then we're going to get then 1 over n. So we've got, this is the, we're going to solve this for b naught and b1. We've already got the solution to b naught already, so we can plug that in. So again, we're going to solve this for b hat and b1. So we're going to set this equal to naught. Wait, it's frozen. One second, technical issue. Doing this. One minute. Oh, I know why. Oh, sorry, I'm being silly. We're back. Okay. Oh, we just lost all of that. Okay, sorry. Anyway, we're back. Okay, so we got from that the solution for b hat naught b1. For any b1, the solution is y bar minus b1 x bar. We can then take the first order condition for b1, and we're going to get now sigma xi yi minus b naught minus b1 xi equals naught. Okay, so we can plug, and again we're solving this, so we're going to solve this. We've already got b hat naught, the optimizer for b naught given b1. We can plug that in. So we've plugged this into T. Remember, we're going to solve for b hat naught and b hat 1. So we're going to get then sigma xi yi minus y bar. So this, I think this is a lot quicker than the solutions online, I think. So then we're going to get, and then plus, so we subtract off again, we're going to subtract off this b hat given the b naught 1. So we're going to subtract, we're going to add b1 x bar. So that's going to give us minus b hat 1 xi minus x bar, plugging in the solution for to the first order condition. I'm going to set this equal to naught. Well, when we do that, then we're going to find b hat 1 is sigma I equals 1 to n, all these. Sigma I equals 1 to n xi yi minus y bar divided by this of okay, and then we've then got our solution for this. Of course, then to get the estimator for b naught hat, we just plug in this, which is by definition just then b hat naught. This is the optimizer. Okay, then we solve them both. All we're doing 2 equations and 2 unknowns here. And again, remember the trick that this is equivalent to sigma I equals 1 to n. But what this is it anyway, but it's equivalent to this. So you can write it either way. They're going to have the same number. And again, you can see this here. Just to rewrite it equivalently, then you can use the trick. And we went through this in the extra. We did it in tutorial. We did it in the extra lecture, and it's also in the derivations. It can be done a lot quicker though. And again, we can multiply top and bottom by 1 over x. You won't change anything. And what we can see is that the top part is the sample covariance between y and x, and the bottom part is a sample variance of x. Okay, so then, and then we can then obviously once we've got our b hat 1, we can plug it back in. This is then the optimal estimate for the intercept. So that's the OLS estimator for a model with an intercept and 1 regressor, and we can see the only assumption we need is that xi isn't a constant, because if it was, that would be not. That's just saying there's no perfect multiple linearity. Because we've only got 2 regressors here, then the only way we're going to include the same variable twice is if we include another variable which is also constant. So again, the intercept is still a variable. I know it's a bit weird to say, but it's still an included regressor. It's just a variable that takes values 1 everywhere. So xi can't be constant, otherwise you're going to include the same variable twice. And of course, you can see here you can't solve for this unless this doesn't equal naught. And if xi was constant, then xi equals its mean, and therefore this would be naught. So that's the only thing you need. The only thing you need for the OLS estimator to exist is a no perfect multilinearity. So again, we can always do this. What this estimates and what it does, of course, depends upon the properties of the true model, but the definition holds in general no matter what assumptions hold on y and x. We can also generalize this to when we've got a general vector case. So we can then, so that's it, that's all you needed to do for question 1. And the reason is, and remember we talked about this at length now, the reason we can see that OLS, the first order conditions, what it does is it chooses the parameters to make the sample residuals uncorrelated with x, and that's what's going on here. What this look at the first order condition. This here is the residual, estimated residual, and this is x, and it's forcing the covariance between x and the residuals to be naught. And that makes sense. If we believe at the true parameter that the covariance of this unobservable epsilon and x was naught, then the best thing we can do is to enforce that in the sample. So the properties of OLS, of course, it's only going to be consistent if the true model is linear and we have that the population equivalent of this holds, that at the true parameters the sample covariance of x and epsilon is naught. So this all generalizes to the multivariate case as well, when we've got a general number of regressors. But we won't do that for now, because we've got quite a bit to get through. But this, so you can generalize this, and what happens is when you've got multiple regressors, you can have a first order condition for every slope coefficient, and it's going to choose the parameters to make the residuals uncorrelated with all of your regressors. So that's what's going to happen when you've got multiple regressors. Let's say you've got p slope coefficients. You're going to have a first order condition for each, and each first order condition is going to be choose the parameters to make the estimated residuals uncorrelated with each one of the regressors. So you can actually generalize this and put this into its matrix vector form and solve for it in general, and that's what you'll see if you go on to do more advanced courses. I mean, we could even do it now, but we'll leave it for now. It's not that hard really, and I think it actually makes it easier once you see all this in general matrix and vector form. But we'll leave that there for now. So that's all you need for question 1. So question 3, one of the assumptions of order least squares is that the population model is linear in parameters. Explain what is meant by this. Okay, so again, the OLS estimator is just a mechanical definition. One of the key assumptions we need in order for it to unearth the parameters to the true model is, of course, that the true model is linear in parameters. So it looks like this, where again, now these are the true parameters. So let's put a naught on them here to denote that these are the true parameters. Okay, here, when you specify this linear model, for every different value of the parameters, you're going to get a different residual, and we can choose these to minimize this sum of squared residuals. But the idea is that there's some true model which generates y, and you think of this here as the true effect of x on y in the true model. If it's the case that at the true parameter, the covariance of this unobservable, everything else that drives y, is uncorrelated with x, well, this implies that this true parameter, we did this in the tutorial and the extra lecture, is the covariance of y, the population covariance of y and x divided by the variance of x. Okay, so this is the population value if it's linear, population coefficient, if linearity holds and this exogeneity condition holds. Okay, so the linearity assumption is that y is a function like this, and linear in parameters means all the parameters enter linearly, and that's it. So that means you can't see any of the parameters are in a non-linear function. Xi could be anything. So xi could be, say, the log of some other variable zi. So it doesn't matter whether x is some linear function. It doesn't matter if your regressors are some non-linear function of some other variables. All that matters is that the parameters, these are marginal effects, all enter linearly. So for example, this wouldn't count. You can't have yi equals, say, 1 divided by, say, b0 plus b1 xi plus ei. That's not non-linear. This is non-linear. This is now a non-linear function of the parameter. Okay, so it's just got to be linear in. It's got to be a function of. It's got to be a function that's linear in the parameters. Namely, when you differentiate y with respect to the parameters, it should then not be a function of the parameter. This is beneficial because when we take the first order condition, if this residual here was, if the fitted model was a non-linear. When you take this first order condition, you wouldn't be able to. Yeah, I mean that's fine. Yeah, that derivation's a full derivation for the exam. Yes, all that's left is you'd have to explain why this held that bit. It depends how technically it doesn't matter really whether you state it's this or the other one because they're both equal to each other. But if a question asks you to, you can divide out the 1 over n's. if a question just asks you to derive the OLS formula for the OLS estimator, well, technically either one is correct, of course, because they're equivalent. If a question asks you to establish that the OLS estimator is this, well, of course, you've got to show that this equals this by using that trick. Okay, and remember, so you can show this, we can do it again. Yeah, all that's fine. The only thing that's left is, if it asks you to show specifically it equals this, you've of course got to mention why these two are equal to each other. And remember, so we can write that down here. So remember the trick. You can see it. We'll do it again. So we've got sigma xi yi minus y bar, and what we're saying is that we can rewrite. If we expand this out, we're saying that this equals sigma I equals 1 to n xi minus its mean. So I think the derivation on the Moodle is fine. It's the same in Word. It's a bit long-winded. You don't really need to go to that full yi minus y bar. So we can see that. So that we're going to prove this, that the two are equal. So of course, to do that, all you've got to do is expand this out and just show that both sides are equal. So if you expand out the right hand side, well, the sum I equals 1 to n xi, if you expand this out, it's just equal to sum of xi times that bit, which is going to be the sum of xi yi minus y bar. This is just this bit here. So of course the next term is going to have to equal 0 if these two sides are equal. Plus minus sigma I equals 1 to n of x bar times yi minus y bar, but the x bar is constant, so it can come outside. Yi, yeah, x bar, it's the average of n terms, but it's just a number 1, 2, 5, whatever. It's just fixed. It's not varying. The mean of x doesn't vary across I. Of course, it's the average across I. It's some fixed number. The last term is then not, because, well, the sum of yi, if you expand out this sum of yi, but you're going to get the sum of yi minus the sum I equals 1 to n of y bar. Well, this here is just, because y bar is constant, it's going to be y bar added together n times. So it's sigma I equals 1 to n yi minus n times y bar. And this is not, because remember, by definition, y bar is a sum of y over n. And that's it. All we've done here is expanded this out and shown that actually it just equals this part, because this bit is going to equal not because of this. Okay, so you can see you can do that really in such a few lines. So then that's the only bit, is to that last bit, and of course then the same thing holds for the xi squared bit as well. Okay, so hopefully that answers that. We've seen that a few times now, that trick. Okay, so going back then, so the linear in parameters, I mean, it's literally as it sounds, that the regression function is just linear in the parameters. So that these can only enter like this. It can't be like this. Doesn't matter that it's not saying that the relationship between y and x is linear, because you could have xi squared as well. It's not saying that. You could have b2 naught xi squared or whatever else. So the relationship between y and x can be non-linear, but that whatever that relationship is has to be expressible in some linear function of variables of x. Okay, so you could have anything added. You could have, say, a b3 naught whatever log xi. You could add anything. So that can be. It's got to be a linear. So you can't have. So that's fine, but you can't have this, because of course in here b0 and b1 the parameters don't enter linearly, and we take the derivative of this, it's going to depend upon x, whereas the derivatives sorry, when you take the derivative of this, it's going to depend on the parameters b0 and b1, whereas it doesn't here. So the benefit of this is not that it's necessarily realistic, is that it just helps to it makes, if you assume a linear model, then we can use then when we do OLS, which is suited and tailored for linear models, then it makes solving for the parameters much easier. And there's also a closed form solution. If you've got a nonlinear function, these first order conditions, when you minimize the sum of squared residuals, will then not be uniquely solved, and it won't have a closed form solution in general, so therefore you have to solve them implicitly by numerical method. So this is another reason why these linear models are popular historically, is because of course in the 70s, 60s and so on, it was very difficult to compute even the linear models, especially for large sample sizes. So therefore it just made it a lot easier to assume this, but now of course it's much easier to work. You can solve you can extend all this to the nonlinear case, and the first order conditions can all be solved numerically relatively fast. Okay, so that's just the benefit. That's why these were studied a lot in the past, is because they were just a lot easier to work with, and they was much easier to compute in practice. Okay, so then hopefully that's clear then on the linear in parameters bit. So next bit then is just asking you to work through this idea. So this is going to be verifying whether or not the exogeneity condition holds. Remember, so we assume linearity, linear in parameters, so that's one key assumption we need for OLS to be consistent and unbiased. And that's fundamental, right? Because the OLS estimator, of course, it's assuming a linear model. So we want the true model to be linear. It doesn't have to be, but if it is, then of course OLS is going to have... If it's non-linear, then OLS can't in general be consistent estimates of B0 and B1. The next assumption then is, how can we identify these parameters B0 and B1? What are the true effects? Well, if we assume then that at the true parameters B0 and B1, that the covariance of this unobservable with X is not, well then we can work out what these true parameters would be. If it's not the case, and there is a correlation between the errors and X, well then the OLS estimator will be biased. And we're given, the classic example is of wages and schooling. So if you look at, and again it all comes back to how do you want to, let's say we regress wage on, that's the classic example, wages on say alpha naught plus, just give them different names, and these are the true parameters now, whatever they are, plus EI. Well, it all comes down to how you want to, if you assume the OLS condition here, the exogeneity condition, well, it chooses another way of thinking about that is, the exogeneity condition assumes that at the population level, the covariance of this unobservable and X is not. And you can choose a B0 that's consistent with that by just plugging it in. Remember, you can solve for, this is what this actually does, that's what it's saying. If you assume this, in this model here, the exogeneity would assume that the covariance of the unobservable EI, everything else that drives wages, and your years of schooling equals naught. Well, if you assume that, you can, and you assume linearity, if you put these two things together, you can, if you assume these two things, you can actually you'll find that B0, and we did this, is just going to be the population covariance of W and S, wage and schooling, divided by the variance of S, assuming of course the variance of S isn't naught, namely that schooling does vary, which of course it will. This is what the true effect would be if these two assumptions held. That means then how you interpret B0, well, what this B0 has been selected at this value of B0, this SI and E, this epsilon are uncorrelated then. At this value of B0, we know that this holds because we've used that to solve this. So that then the two things give us the same thing. B0, if we evaluate this at B0, this particular B0 here, well, by design, EI and SI are uncorrelated. That means then how you interpret B0, if we change schooling by 1 year, then B0 would be the average change in wages when EI doesn't move an average, and it doesn't because we've selected B0 such that SI and E are uncorrelated on average. So if you change SI by a small amount, EI will not move. It's not that EI won't change, it just won't be changing in any consistent way with SI. On average, it's going to move not. So they're going to be uncorrelated with each other. Okay, so there's not going to be any persistent movement with each other. So if they're positively correlated, when one goes up, so would the other. We've set them to have zero correlations. That means when there's a change in schooling, on average, the epsilon I doesn't move with it. It just, on average, is going to be not. Well, that's fine if we believe that's representative of what's going on in reality, but then we also know then that in reality, when schooling, say, increases by 1 year, so will their natural ability on average, and we know that's going to lead to the higher wages, namely that this unobservable is going to be higher. But we've ruled that out. We've selected B not here, forcing the covariance between the two to be not, but that's not what's going on in the true model. And if you do that, you're going to overestimate B naught. B naught is going to be an overestimate of the true effect of schooling on wages. If you want to work out the effect of schooling on wages holding ability fixed, well, that doesn't do that, because here, when schooling goes up, so does ability, and therefore wages are going to be higher. But we forced in our model schooling and ability to have basically no correlation, which doesn't happen. Okay, and that's the idea of it then, is that if we want this B naught, we want to get the effect of schooling on wages holding ability fixed, and we've got to control for it. If we control for ability as well, and we run this regression, W alpha naught plus B, let's say we could measure it, plus EI, so it will be different, and call it VI, so then we run this model. If we could run this and do OLS, enforce the OLS assumption, the exogeneity condition, choose these parameters to make W and, sorry, that should be schooling, that should be ability here. Let's say we could measure natural ability then. If we could do this and choose B naught and gamma to make S and A both uncorrelated with V, we're going to have two of these. If we tune the exogeneity condition, we can work out B naught and gamma naught, lambda naught, that makes schooling and ability uncorrelated with V. Well, that means now then, when you now because the gamma naught has been selected to make AI and VI uncorrelated, now the new unobservable doesn't change with VI, with ability. So when schooling goes up, then ability will change, but now it doesn't matter because in the error term, VI, the new unobservable, isn't moving with ability. So once you've controlled for it, you've taken out that reverse causality. Now when schooling changes, it's not changing anything in the unobservable term. And therefore you can now interpret this effect as the effect of schooling on wages holding ability fixed, because in essence you've forced the unobservable now to not change with ability. And that's the idea of it. So the notion of a bias is when you've omitted something, if at the true parameters it's going to be the case that our regressor is going to be correlated with the unobservable. In this case, in the wage schooling, we'd expect a positive co-movement between the unobservable and schooling, because when schooling changes, then their ability is higher and they're earning more, so the unobservable is going to be higher wages. But if you don't control for that, you're going to attribute all of that to the effect of schooling on wages. So the B naught will reflect the direct effect of schooling and all of the effect that comes from the ability being higher. So the unobservable is going to be higher, namely the wages are higher. Okay, and remember that's what OLS does, right? It fits a line to a set of points. So when schooling's higher, in this model where we've just got one regressor, when we've just got wages on schooling up above here, if we just run this regression up here, let's say now let's think about what OLS does when you do it in practice with a data set. You're gonna, if you just fit a regression line here without controlling for ability, well, what's going to happen when schooling's higher, then wages are higher, not just because of the direct effect of schooling, but because this residual is going to be, this observable is going to be higher because of this high natural ability, namely that W is going to be higher. So when schooling goes up, wages are going to be higher than they should be just from the direct effect of schooling. The direct effect of schooling could be quite small, so it's going to, so when schooling increases, there's going to be a slight increase in wages from the effect of schooling, and then a big increase in the effect of mobility. And OLS is going to choose a parameter to fit the set of lines to fit the curve, the line, to that set of points. Now, because wages are a lot higher than they should be, well, OLS is just going to attribute all of that to school. It's going to increase the coefficient on B0 and make this line fit to the set of points. But the wages are higher than they should be, because we've not controlled for natural ability. So if you want to look at the effect of schooling on wages holding ability fixed, and of course this linear regression can't do that, because at the true parameter these two are correlated. Okay, so we said that a few times, but that is fundamental. So then that's always the thing when you're talking about whether or not OLS will be biased or not. Well, first off, just let's assume linearity holds. Well, the only thing left to then verify is whether or not the errors are correlated with each other. If there's a positive correlation between the regressor and the residual and the unobservable, then broadly speaking there'll be a positive bias and negative otherwise. In a one variable model, it will always be the case that if there's a positive correlation between the error unobservable and the regressor, there'll be a positive bias and a negative bias otherwise. And it kind of makes intuitive sense as well. So we're going to apply this to an example then. So we're looking at so we've got a justification for job training that they improve work productivity. Suppose that you're asked to evaluate whether more job training makes workers more productive, and you've got a data set on the total hours worked at manufacturing firms in Birmingham. In particular, for each firm, you've got information on hours of job training per worker. This would be the X value, the regressor, and number of non-defective items produced per worker hour. So the output, this would be the Y variable. So you've got a measure of their productivity and a measure of how much training they've had. So the question A, what simple linear regression might you use to investigate this relationship? Okay, so it should be a bit clearer here. I mean, so you might start with a linear model, yi equals a constant plus b naught xi. So I mean, you would start with this. This would be then the simple linear model. Well, that's the only linear model that you can come up with a constant with one regressor. We've not got any. It's not saying we've got any other regressors here. So this would be a candidate linear model. What major assumption must you make regarding the relationship between the regression and the error term? Well, it should be a bit more specific. It means if you use OLS, and if we've got a sample from let's say we've got a sample whatever n, could be 50 or 100. It should really say if you use the OLS estimator, what assumption must you make regarding the relationship between the error and x in order to get unbiased, or well, to get consistent inference. So it probably needs a bit more detail. But again, so with that in mind, so if we want to use OLS and we assume the linearity holds, well, we know the key assumption for consistency is that the covariance of EI and XI is not. In our example, that all the other factors driving productivity are not correlated with the total hours of training. So linearity plus this exogeneity, the key conditions for consistency. Of course, we always need no perfect multilinearity. So that's needed for any result, because we need no perfect multilinearity for the OLS estimator to even exist. So we always assume that. So once that holds, the only two we need this covariance assumption, and again a random sample to get the weak law of large numbers. But it's this, when we talked about in the tutorial, it's this assumption that's key in underpinning consistency. If there's some correlation between the error, the unobservable E and X, well, we're going to get this bias for the reason we gave in the wage schooling example. So that's what it's getting at here. This is the major assumption, the exogeneity condition. Once we assume linearity, that's the key thing left to verify that OLS will be consistent. Okay, so what are so the next bit's getting at what are the potential emitted factors. So EI, remember, let's say that the true model could be, so we've got say productivity, maybe call it PI, productivity. So right equals a constant plus B naught, say hours of training. Well, there could be many other variables, right, which are going to be driving the worker productivity. And again, of course, it's going to also be a function of kind of the underlying skill set or ability of the workers. That would be one of the key ones. And there's going to be many other factors, right? So it's what this is getting at is we don't really believe that it's just the hours work that's going to drive their productivity. So namely, if you look at the effect of productivity of training on productivity just without any controls, well, you're going to get a similar issue to what you've got in the wage schooling example, that you're not going to control for the fact that when they have more training, it's more likely to be in a workforce where you've got a higher ability workforce. They could also have potentially then possibly say higher underlying education and previous training levels. Okay, and it could be a better managed firm and so on. So you see, there could be many, and again, you can't state all of them. You'd have to pick out the things that the researcher would really want to control for. So it's that once they've controlled for all these other factors like underlying ability and education and previous training, we can then run OLS and we can interpret then B0 as the effect of extra hours training holding these other fixed. Okay, plus VI. So the point is that these would be, if you just run a regression of P on T, well, all this would be your error term normally, so call this EI. If you just run this, if you just regress P on a P productivity on training, and well, you can think of break up your error term into these parts. So the true model could be this line here, where VI is uncorrelated, where VI is exogenous. Once you control for them, then VI is uncorrelated with everything in there. That would then be your error term. But if you just regress on this part, well, you've omitted these variables. So then you start to look at what is the correlation between your omitted variables and your included variables. So again, we want to look at, of course, what's the correlation between the unobservable and the regressor. Well, we've got to think what are the other variables that are in this unobservable, and of course, it's everything else that's driving productivity. And so you just keep so we can imagine here that the correlation between underlying ability, underlying education and training and management quality and so on is going to be positively correlated with how much training they're given, and you'd imagine that both of these effects are also going to be positive. What that implies is then is that the covariance of the unobservable and training is probably going to be positive, which is part C. So then, do you believe that this unobservable EI is likely to be uncorrelated with the regressor? Well, probably not, because we've not controlled for underlying ability and so on, quality of management, the type of firm and so on. All of these things are likely to be positively correlated to how much training they've got. Another way of saying that is if you just look at the OLS effect of training on productivity, you're going to find when they're trained more, they're also going to be working at better quality firms with better abilities and probably higher education levels and so on, which means they're going to be having higher productivity, not because just the training, but because of all these other factors. And if you just regress just on that one, if you just regress just on training, it's going to pick up all of that in beta naught. Okay, and that's the notion then of this exogeneity condition holding. So again, and these types of questions are always the same thing. You first have to state what are the key assumptions we need for OLS to be consistent. Well, it's linearity and this exogeneity condition. Then the question will start to get you to look at what is it that's possibly, what else is driving the independent variable that we've not controlled for, i.e. what else is in this unobservable, and then talk about, do we believe that these omitted variables, are they going to have a positive, are these omitted effects going to have a positive correlation or a negative correlation with TI? Okay. And that's it for question 4. Are there any questions on that? So we've seen that a few times now. We've talked about that in depth really a few times. That's the key idea that's underpinning